Up till now, we have discussed different techniques of integration like substitution method to find the integral of the function. Now here is another uh, method by which you can solve the integral, that is basically integration by parts. It is a special method of integration that is often useful when two functions are multiplied together. Like you can see two functions are multiplying in. These are the examples of the functions where two functions are multiplying, and we can solve them by using integration by parts. Now, this method is based on the product rule of differentiation. Suppose that u and v both are differentiable functions of x, then the product rule in the terms of differentials give us d of uv equals to u dv plus v du. Rearranging this rule, we can write u dv equals to duv minus v du. Integrating both sides with respect to x, we get integral of u dv equals to uv minus integral of v du. This is basically the formula for integration by parts, and our goal is, when using this formula, to replace one integral which is on the left with the other one which is on the right side, which can be easier to evaluate. Now, as we have to select u and dv, so for that the acronym ILATE is good for picking u. So the key thing in integration by parts is to choose u and dv correctly. So ILATE stands for inverse trigonometric functions, logarithmic functions, algebraic functions, trigonometric functions, and exponential functions. The closer a function is to the top, the more likely that it should be used as u. So in integration by parts, we proceed in 3 steps. First, we choose u and dv, then we differentiate u and we integrate dv. Then we put u dash, dv, and v into the formula of integration by parts, and then we simplify and solve the expression. So we can say the moral of the story is to choose u and dv carefully. So choose a u that gets simpler when you differentiate it, and dv that does not get any more complicated when you integrate it. So here is an example where two functions are multiplying. One is the trigonometric function, other one is the algebraic function. So expression is already in the format of integral u dv. So we have to select u and dv. So u is algebraic function according to that ILATE rule, and the remaining term dv is the remaining function is dv, comes under dv. So we have to differentiate u. So the derivative of u is du equals to dx. We will integrate dv, that is v is equals to sine x. Substituting all the values in this expression, u is equals to x, so x is written here, v is equal to sine x, so it's x sine x minus integral of v, so integral of sine x into dx. Integrate sine x, we get minus cos x, so the answer is x sine x plus cos x plus c. So c comes because this is an indefinite integral. Now comes another example in which there is ln x divided by x square. Once again, two functions are multiplying. One is ln x and the other one is um, x square dx. So we have to choose u and dv. Let u equals to ln x and dv equals to 1 by x, 1 by x square dx. Differentiate u, the derivative of u will give us 1 by x into dx, and integrating dv gives us minus 1 by x. Substituting all the values in this expression, this gives us ln x into minus 1 by x minus integral of minus 1 by x into dx by x. So by simplifying them, we get minus ln x by x plus integral of dx by x square. Taking the integral of 1 by x square, it gives us minus 1 by x plus some constant of integration. Now comes the tabular integration. It is a special technique for integration by parts that can be applied to functions of the form g of x into h of x, where one function can be differentiated multiple times with ease and the other function can be integrated multiple times with uh, ease. In problems involving repeated applications of integration by part, a tabular method is more useful and it can help to organize the work. This method basically will work. This will work to avoid tedious algebraic details that may come up as a result of repeated iteration. Um, tabular integration can be used as a viable substitute for integration by parts when you have a terminating U term. So here are the steps for tabular integration. In the product comprising the function f, you have to identify the polynomial and denote it by f of x, and call other function as g of x. Then you create a table for f and g functions, and you differentiate f of x until you reach 0, and you successfully integrate g of x the same amount of times. Now negate every second entry under f of x and construct the integral by taking the product of f of x and the first integral of g of x. Then add the product of f dash of x times the second integral of g of x. Then add the product of f double dash of x times the third integral of g of x, and so on. Let's apply this method on this particular example, which is x cubed sine of x dx. Now here, this function is a product of two functions. One is x cube and the other one is sine x. So one is an algebraic function, other one is a trigonometric function. So f of x function is x cube and our g of x function is sine x. So we have to differentiate x cube and we will integrate the trigonometric function. Now, as I have told you that u is x cube, u is x cube, or f of x is x cube, we make two columns, putting u in the left column, and in the left column list all the derivatives until 0 is reached, and in the right column basically begins with d of v, that is equals to sine x, and list all the integrals down to the same level as the 0 in the left. Now pair the first entry of the left column with the second entry of the right column, then the second entry of the left column with the third entry of the right column, etc. Do this until no more pairs can be made. It might be helpful to draw in arrows to see the pairing as follows. Now after this, add these pairs with alternating sign beginning with positive sign. So the first pair is minus x cube cos x, then comes minus 3x square cos x, sorry, plus 3x square cos x, 3x square sine x, plus 6x cos x minus 6 sine x, plus the constant of integration. So in this manner, you can do integration by parts many times, and it is much simpler to solve like this, in this manner. Now let's discuss some more examples of integration by parts. Here, once again, we can see that this integrand is the product of two functions. One is x square, other one is e raised to the power x. Now, let u is equals to x square. The remaining function will come under d of v. So the remaining function is e raised to the power x dx. Take the derivative of u. So the derivative of u will become du equals to 2x dx. Here is the derivative, and integrate dv. So it becomes v is equals to e raised to the power x. Now, the question is already in the form of integral of u dv. So just apply the formula of integration by parts, that is basically u into v minus integral of v into du, substituting all the values of u, u dash, dv and v into the formula of integration by parts, which is this. Simplify it and find the integral. So value of u is x square. X square is written over here. Value of v is e raised to the power x. So this is uv minus integral of v. So the integral of v is e raised to the power x into du. That is basically 2x dx. As 2 is a constant, you can take it outside the integral. Now you can see here, once again, you are getting a product of two functions, that is x into e raised to the power x dx. So you can again apply integration by parts. So applying integration by parts, once again, select u and dv. U is x and dv is e raised to the power x dx. Differentiate u. So du equals to dx, integrate dv. You get v is equals to e raised to the power x. Substitute all the values in the formula of integration by parts, that is integral of u dv equals to uv minus integral of v du. Substitute all the values in the expression, I get this. Now integrate e raised to the power x. So the integral of e raised to the power x is the same, e raised to the power x plus some constant of integration. Now substitute all these, write this answer, replace this expression with this answer, we get this. So this is the integral of answer of the integral x square e raised to the power x dx. Now here is another question, that is e raised to the power x into cos of x dx. Once again, the integrand is a product of two functions. One is the exponential, other one is the trigonometric function. So let u is equals to e raised to the power x, and the remaining function comes under dv. Differentiate u and integrate dv, we get these answers. Now applying the formula of integration by parts, u into v minus integral of v into u. Now we can see that on the right side, once again, I am getting an integral, so I have to apply integration by parts once again. Now let u is equals to e raised to the power x and dv is equals to sine x dx. Differentiate u and integrate the expression dv. I get these answers. Substituting all these values in the formula of integration by parts, I get this expression. Now, as we all know that we have already solved this expression. It's already on the left side. So taking it, moving it towards to the left side, I get 2 times of this expression plus these functions plus some constant of integration. Moving to the right side, I get this answer. So this means that uh, you can apply integration by parts many times in a single question. Now here is another question. Find the area of a region that is bounded by the curve y is equals to x e raised to the power minus x and the x-axis from 0 to 4. So this is a question of definite integrals. Integral from 0 to 4 x e raised to the power minus x. Once again, this expression is a product of two functions, so we can apply integration by parts. Let u is equals to x. Let the remaining functions be equals to dv. Differentiate u while integrate dv. I get these answers substituting all the values in the formula of integration by parts, that is u into v minus integral of v into u. So this is already the answer, but here we also have limits of integration. So upper limit minus lower limit, I get this expression. On the right side, I have to take the integral of e raised to the power minus x. So the integral of e raised to the power minus x is minus e raised to the power minus x. So this is the integral. Now you have to apply the limits. After applying the limits, I get this expression, and after simplifying, this is the answer. Now let's moving towards the next example, x square into e raised to the power x dx. Instead of using integration by parts again and again, let's apply the tabular integration. Now let's take f of x equals to x square, because we can differentiate this expression easily and it ultimately goes to 0, and the other expression g of x is e raised to the power x. Now we have to take the derivative of f of x and we have to take the integral of g of x. X square is the function whose derivative we will take, and e raised to the power x is the function whose integral we'll calculate. So the derivative of x square is 2x. Integral of e raised to the power x is e raised to the power x. Derivative of 2x is 2. Integral of e raised to the power x is e raised to the power x. Now derivative of 2 is 0 and integral is e raised to the power x. Now pairing them. After doing pairing, apply the alternate signs, we get this answer. X square e raised to the power x minus 2x into e raised to the power x plus 2 into e raised to the power x. So this is the answer of this is the answer by tabular integration. Same comes when you apply that traditional uh, integration by parts formula. Now let's discuss some exercise questions, like question number 4, integral of x square sine x dx. Once again, the integrand is the product of two functions. One is the algebraic function, other one is the trigonometric function. This is basically the ideal case in which we can apply the tabular integration, because in tabular integration one function should be some algebraic function, because when you take its derivative it ultimately goes to 0. So here we'll apply the tabular integration. This is f of x, this is g of x. Take the derivative of x square. Derivative of x square is 2x. Once again, derivative of 2x is 2 and derivative of 2 is 0. Now integrate sine x. The integral of sine x is minus cos x. Integral of minus cos x is minus sine x. Integral of minus sine x is plus cos x. And integral of cos x is sine x. Now pairing them, starting with positive sign, apply alternate signs. So positive, then negative, positive, then negative. Now multiplying them, minus x square cos x plus 2x sin x plus 2 cos x plus constant of integration, because when you multiply these two, you'll get 0. So we get three terms plus some constant of integration, just because this is an indefinite integral. So like this you can apply tabular integration. This is much more easier than applying integration by parts. Now this is once again a simple question. 4x into secant square 2x dx. Let y is equals to 2x. Then dy equals to 2 dx. So y into secant square y dy. Now doing integration by parts, because once again it's the product of two functions y and secant square y. So y into tan y minus integral of tan y dy. So integral of tan y is ln of secant y. Doing back substitution, you get this expression. Here once again you have a product of an algebraic function with an exponential function, so you can apply the tabular integration. F of x is r square plus r plus 1, whose derivative we will calculate, and e raised to the power r is a function g of x, whose integral we will calculate. So the derivative of r square plus r plus 1 is 2r plus 1, derivative of 2r plus 1 is 2, and derivative of 2 is 0. Now taking the integral of e raised to the power r is e raised to the power r, e raised to the power r, and e raised to the power r. Now pairing them. While during pairing, we have to use alternate signs. Starting with a positive sign, the next will be a negative one, then comes the positive one. Now multiplying them, both of them, we get r square plus r plus 1 into e raised to the power r minus 2r plus 1 into e raised to the power r plus 2 into e raised to the power r plus some constant of integration. This is the answer of the um, integrand, but if you really want to solve them, you can simplify them like this. But there is no need to simplify them. Now comes question number 24. E raised to the power minus 2x into sine 2x dx. Doing some substitution, let y is equals to 2x. This means taking the derivative of both sides, dy, du or dy is equals to 2 dx. So what will be our expression? Our simplified expression will be 1 by 2, as we have only dx. So taking 2 on the left side, so we get 1 by 2 into integral e raised to the power minus y sine of y dy. Let this be equals to I. Okay. Now once again, uh, we are getting a product of two functions. We can apply integration by parts. Let u is equals to sine y, du is equals to cos y dy. Taking the derivative of u, and the derivative of u is uh, du equals to cos y dy, and integral of dv is v equals to minus e raised to the power minus y. Now substituting the values in the formula of integration by parts, I get this expression. I equals to 1 by 2 into u into v minus integral v into u. So minus minus becomes positive. So this is the expression. Now we can see that on the right side, I'm once again getting an integral. So once again, I can apply integration by parts. So once again, applying integration by parts, let u is equals to cos y. So the derivative of u is minus sine y. The remaining expression comes under dv. Take the integral of this expression, you get v is equals to minus e raised to the power minus y. Now substituting all these values in the integration by parts formula, I get this expression. After simplifying it, we can see that we are getting this expression again. As we have solved this expression and we have solved this expression, this is equivalent to I, so I have um, replaced it with I is already on the left side, I is on the right side. Taking I to the left side, I get 2I equals to this expression. Taking I to the taking 2 to the right, I get this expression. So we get this answer. Here the things were not terminating. Integral were repeating again and again, and when we applied integration by parts for the second time, we got the same integral, which was the question. So instead of we substituted it equals to I and solved the expression. These are some more questions on integration by parts. I hope you can solve them now. Easy questions. This is once again the same question, like e raised to power theta into sine theta d theta. So let I is equals to integral of e raised to power theta sine theta d theta. Let u is equals to sine theta. Taking the derivative of u, we get cos theta d theta. The remaining term comes under dv. Taking the integral of dv, we get v is equals to e raised to power theta. Substituting all these values in the formula of integration by parts, I get this expression. Now, as we can see that integral comes on the right side once again, so we have to apply integration by parts once again. So let u is equals to cos theta, derivative of du is minus sine theta d theta. The remaining terms comes under dv. Integrating dv, we get v is equals to e raised to power theta. Now substituting all these values in the formula of integration by parts, this is this comes as it is, minus applying integration by parts formula here, I get this expression. Now we can see that this is the same as the question and it is equals to I. So I'll substitute it equals to I. I'll replace it this with I. So replacing this expression by I get this. I is already on the left side. Taking it toward to the left side, I get 2I equals to this. Now taking 2 to the right side, I get this expression. So this is answer of integration by parts. Now questions are simple. I have solved many questions of the exercise. I hope after listening to the theory of integration by parts and um, after that I keyword, you can solve the questions based on integration by parts, and you can also apply the tabular integration to solve the integrals.